This video is about analyzing electric circuits using Thevenin analysis. Here's a picture of Leon Thevenin. He studied Ohm's law and Kirchhoff's law and then extended them to analyze complex electric circuits by reducing them into simpler circuits. Any linear network of resistances can be reduced to one equivalent resistance. Thevenin's theorem converts a complicated circuit into a simple circuit with one voltage source in series with one resistor. When the load is connected to the Thevenin equivalent circuit, it behaves exactly like it did in the original circuit. That load can be anything from a motor to a computer chip. Here's a circuit with two batteries and three resistors. Let's call R3 the load and find the voltage across and the current through it. The first step is to remove the load resistor. I'm going to mark the terminals where the load resistor was with A and B. That way we can talk about them. The next step is to find the Thevenin voltage, or VTH. The Thevenin voltage is the voltage across the points A and B. If we call the voltage here 0 volts, this battery forces this point to be at minus 30 volts. And this battery makes this corner positive 10 volts. The total voltage across those two resistors is 10 minus a minus 30, which is 40 volts. That gives us a current flowing through them of 40 volts divided by 6 plus 12, or 18 ohms. And that's 2.22 amps. .22 amps flowing through a 6 ohm resistor in this direction . 2.22 amps times 6 ohms equals 13.3 volts. That means the voltage drop across this resistor is 13.3 volts. Ten minus 13.3 is minus 3.3 volts. Well, the voltage drop A minus B is a minus 3.3 minus 0. That's if we draw it in this direction. If we reverse the polarity of the battery, we can make that a positive voltage. The next step is to find the Thevenin resistance. The Thevenin resistance is this resistance here, which is the resistance between points A and points B. To do that, we need to remove the sources and replace them with their internal resistance. Since these were both voltage sources, I'm going to replace them with wires because the internal resistance of a voltage source is ideally 0. Now we're ready to find the resistance between point A and point B. I'm going to fold point A out and point B out to make this more obvious. So if A is here, and it's got a wire like that, as we come this direction, we come to a 12 ohm resistor. As we follow the wire along, we get back to B. On this side, we get to a 6 ohm resistor. And the resistor connects to point B with a wire. Well, that's obviously a parallel resistor. So the equivalent resistance there will be 1 over 6 plus 1 over 12, all inverted, and that equals 4 ohms. So our Thevenin resistance is 4 ohms. The final step is to reattach the load resistor. And the load resistor is 4 ohms. Now we have a simple series circuit. Current's going to flow out of the battery and go in this direction. That current is going to equal to the total applied voltage, 3.3 volts, divided by the total resistance, which is 4 ohms plus 4 ohms. It gives us 8 ohms, and the current equals 0.413 amps. As that current flows through this load resistor, it's going to have a voltage drop in that direction, and that voltage will be 0.413 amps times 4 ohms, and that will equal 1.65 volts. And if we map that voltage and current back onto our original circuit, we will have the current flowing up through R3 and dropping 1.65 volts across it. Now it's your turn. Let's use R1 as the load resistor. Press pause, find the voltage and current through R1, and then resume the video to check your answers. The first step is to remove the load resistor and then find the voltage across the gap that's left. In this case, it's 2.5 volts. Then replace the sources with internal resistance. The batteries in this circuit have an internal resistance of 0, so they are replaced with wires. The resistance between point A and point B is the Thevenin resistance, and in this circuit, that's 3 ohms. Reattach the load resistor, find the current through the series circuit, and the voltage across your load resistor. In this case, it's 6 ohms. The current is 0.278 amps, which gives us a voltage of 1.67 volts. And this is what it looks like mapped back to the original circuit.